Hey everybody, welcome in. It is lightning lesson time with Dr. Greg and the Wiz. We are from AI Makerspace, and today you are going to learn the 3 key patterns in generative AI. At AI Makerspace, we always like to align our AIM for the day. So by the end of the session, you will understand how fine-tuning is about teaching the LLM how to act. RAG is about giving the LLM access to new knowledge, and agents are about giving the LLM access to tools. So we want to understand these patterns so we can build really awesome, robust LLM prototypes instead of something that's kind of a mess and just pieced together with stuff we really don't understand. One of the biggest questions we get all the time: should I use RAG or fine-tuning? This is an illusion of choice problem. The answer is yes, you should. You should walk your way through prompt engineering, RAG, fine-tuning, and maybe add some reasoning to your applications in this order. Generally, you're starting off prompting as far as you can go. You're then going to optimize the context of your application in the context window, let's say, before you think about optimizing how your LLM or embedding model should act. You're going to have to do both of these likely to get to a place where you're close to human level performance. And you can use agentic reasoning to really augment any of these. If you look at a simple example, this is from OpenAI's Dev Day last November. It took them a lot of iterations on this particular use case to get to something that was deployable in production, human level performance status. So we kick it off today with fine-tuning. One of the things that we're going to keep reminding you of is that we're talking about patterns, not things. Fine-tuning is a pattern. It's not a thing. It's really the pattern of continuing to train, although it's not exactly continued pre-training. It's about really aligning the LLM to exactly what you want it to do. If you think of the sort of coarse and fine-tuning knobs on a microscope, when we're doing fine-tuning on an LLM, we're getting very fine. We're in the vicinity we want to be in, and we're really dialing in that fine-tuning knob. It's really all about teaching this crazy monster, this LLM, how to act like a person, like one of us, like we would want our assistant to act with us. And there are 3 primary forms of fine-tuning. The first is task training. And task training is all about the behavior of the LLM response. It's really all about what comes out of the LLM. And this is often associated with classic natural language processing tasks, things like write a summary, answer a question, tell me if it's a positive or a negative sentiment. We can kind of think of task training very similar to the way you would want to be able to ask a child, hey, can you go over there and grab that for me? Bring it back over here. You'd want to do it with instructions only, with, say, 0-shot prompting. And that would be really great if we could do that with all the tasks we wanted our LLMs to be able to perform. Right now, it's not exactly possible to do it with instructions only, so we need to give it examples, and that's where fine-tuning comes in. We can train the behavior of the response. We can also constrain the format of the output response, as well as the input. This is potentially very useful for lots of different reasons. One of the things, if you're a developer, like we work with a lot of developers all the time, that you're probably familiar with is JSON. It's a specific format you need to interact with the tools that you'll leverage to build applications. If you're not a developer, then you might think of something like a post on X, former Twitter, or a haiku, something with a very, very specific output format. If you need something like that, you can use fine-tuning to help you get there. You can also constrain the input. Let's say you have only a number of specific product lines that you want to be able to use as input from your data in your company. That can be something that you can do as well. But the third, and the example we'll see today, is associated with language training. It's about actually being able to interpret language, both given as input and in the output of an LLM. And you might do something like try to leverage specific slang terms. You might work in a place, a large bureaucracy or a large corporation that uses all of its own ridiculous acronyms. Or if you're a professional and you work in medical or legal, you know that it's just full of nonsensical jargon that nobody can really understand. We want to show you today real quick that we built a Gen Z translator. That's a lot of fun to play with. We did this by taking the Gen Z data set of exactly what words mean to the rest of us when Gen Z say them. And then we created a bunch of synthetic data using GPT-4. We put it into input-output pairs and fine-tuned an LLM chat model. What chat model did we fine-tune? We fine-tuned Llama 3, the 8 billion instruction-tuned model, which is a great one to pull off the shelf if you're going to get building and fine-tuning today. So the Wiz is going to show us how this works. Everybody, it's time for Gen Z AI. Okay, Wiz, over to you.
Yes. Okay. Thanks, Greg. So basically what we have is a Hugging Face space, and the Hugging Face space is running a front end called Chainlet, which is letting us, key into the model. The idea here is that we can input different queries, and those queries are going to be Gen Z-ified. So we can do things like ask questions. In this case, what we're going to do is we're going to input quotes from, kind of philosophers and these kinds of people. So, I was born not knowing and have had only a little time to change that there. Here and there is a quote from Feynman. And we have, if you know, you know. And then if we use something like change will not come if we wait for some other person or some other time, we are the ones we've been waiting for. You can see that this is going to get Gen Z-ified pretty intensely. I'm going to keep it real, fam. Change ain't going to pop off. If we're just chilling, waiting for someone else to do it, it goes on and on. The idea is that we're able to fine-tune this model, which is not particularly great at this task at the onset, in order to get it very good at the task. And again, as Greg mentioned, the way we do this is by using that fine-tuning data set, which is synthetically generated using a bunch of descriptions. So like a vocabulary of Gen Z words, we're able to impart that information into the model. Now, in terms of the way that it's going here, or the way that this is actually running, again, we're just going to use this simple application file, which is going to point at a Hugging Face inference endpoint, which we can see here, which is running the model. So this is just running that Llama 3 instruct tune model that we fine-tuned, and that's it. You can see that we have this prompt template or header, and that's going to be Gen Z-ify, right? So this is how we're able to key into that pattern that we taught it. And yeah, it's basically just a lot of fun, but it demonstrates one of the key patterns of Gen AI, which is this idea that we can fine-tune our model and shift it towards something, behavior that we're really interested in. And there you go. So with that, I'm going to pass you guys back to Greg.
Yeah, and just so we're clear on this, Chris, the idea here is that we're sort of kind of rewiring the brain of the LLM a little bit to be able to sort of better understand Gen Z. Is that an appropriate way to kind of think about this?
Yeah, exactly. We're teaching it, how these slang terms interact with language, and the idea is that it's able to determine, which slang terms to replace these other terms or ideas with, and we do that by shifting around the LLM's brain or weights. Yeah.
Okay. All right. So if you haven't shifted your brain around for Gen Z yet, maybe you could pick up an assistant like this. There's lots of ways you could imagine using this in your domain of practice. Which brings us to RAG, our second pattern of the day. Now, I'll remind you once more, RAG is a pattern. It's not a specific thing. RAG stands for Retrieval Augmented Generation. And the problem that RAG solves is that LLMs are liars. Off the shelf, they confidently lie, which is the absolute worst kind of liar. And we want to avoid this the same way we avoid it with people. We avoid it by fact-checking people, by finding reference material and pointing to it and saying, that's where I got this information before you give your answer, right? And so finding reference material, adding that reference material directly to the prompt into the context window improves our answers. This is the idea of retrieval augmented generation. And RAG can be broken down into two steps. One is dense vector retrieval, and the other one is in-context learning. Let's see how this works technically. We ask a question. That question is made up of words. We chop the words into smaller pieces called tokens, and we run those tokens through an embedding model. It turns all of our tokens into embedding representations that are lists of numbers. They're vectors. And with those vectors, we can look inside of our database called a vector store. That's going to be full of all of our data that we want to be able to fact check against. We've already chopped it up, tokened it up, and embedded it into vector format. So what we can do is we can look for how similar our question is to stuff in our vector store, in our data. We can set up a prompt template that says something like, use the provided context to answer the user's query. You may not answer the user's query unless there is specific context in the following text. If you do not know the answer, say, I don't know, all right? And then we'll find the similar information. We will return it now, not in vector format, but in natural language, reference 1, reference 2. And this process of retrieval is called dense vector retrieval. The prompt templating and adding of the reference material to the context window allows us to leverage in-context learning. And this is primarily the RAG pattern. However, we haven't gotten to the G yet. There is no LLM chat model until the very end here, where we get our better answer. So we can look a little bit deeper at this, and we can look at how we get this retrieval process done. For those of you without a machine learning background, you'll get some trailheads here. We talked about this idea of taking text and turning it into numbers. You can think about this in the format of these two embeddings quizzes. For instance, where would you put the word apple in this particular image? Go ahead and smash the chat with the answer here. Where would you put apple? And of course, you would put it near bananas, right? And strawberries. And that one's pretty easy. But where would you put the word cow in this little quiz? You might put it probably not at B, right? In fact, puppy is to dog as calf is to cow. And on this X dimension, you might say, we're looking at something like age. And on the Y dimension, you might say we're looking at something like size. But where does Dr. Greg and the Wiz at AI Makerspace fit in on this chart? Where do any of you or where you live fit in on this chart? Where does everything else fit in on this chart of size versus age? Well, we need more dimensions. Most embedding models today have hundreds or thousands of dimensions to try to capture more complexity about what's important to pay attention to in the world. We've been doing this for a long time. The classic example is the word to vec. You can start to kind of understand where that naming scheme came from. This came about in 2013, very classic natural language processing times. Embedding models today are much more complex, although this was proven at the time to be successful on a variety of, quote, downstream tasks. The same idea is still very relevant, trying to create business value with LLMs today. And this is one of the most iconic and earliest examples of dense vectors representing text. Today, we have lots of ways to choose even better models. OpenAI just came out with their best model yet. And of course, Hugging Face has the massive text embedding benchmark leaderboard. As we think about the retrieval process itself, what we are talking about is the same thing we already discussed. We ask a question, we search a database for stuff similar to the question, and then we return that stuff. It's this process right here. And we're doing it with vectors, starting with vectors, finding similar vectors, and then returning natural language. In order to create our vector store, the only thing inside of it is chunks of our data. We take our documents, we chunk them up, we put them all in vector format into the vector store. The retriever itself is a sort of interface that's wrapped around the vector store. It allows us to take our question and go in there, get the good stuff, come back out. Which brings us to the second part of RAG, which is in-context learning. We've probably all been hearing a lot about context windows, and they are very important. What do we put into a context window? Well, of course, we put the prompt. It's very important to give, number one, clear and specific instructions, to give proper context, and to specify with detail what we want the LLM to know. We can give specific examples, or we can retrieve those examples. We've already talked about dialing in the exact output we would want from an LLM. You could prompt this, or you could fine-tune it. So we're talking about this dimension of context optimization when we're talking about in-context learning. But it's not that straightforward necessarily. This is a plot from the Language Models Are Few-Shot Learners paper from OpenAI years ago at this point, GPT-3 paper. And what they showed is that when you used a big enough model, 175 billion parameters, that zero shot, remember that instruction only, worked pretty well, but just one example started crushing it across many different tasks. And as you went from no examples to one example to many examples, it improved the performance. Now, this idea of more and more examples can get us to this idea of a task-specific spectrum. What's interesting is that we can give no examples, one example, 10 to 100 examples. If we go down and we start giving 1,000 examples, what happens? We run out of context window. Well, maybe not today because they're so long, but what if we have to give 100,000 examples? Well, now all of a sudden we're in the domain of fine-tuning. So this all does connect back together in the end. When we move from prompting into fine-tuning, we're moving the examples from the prompt into the trained model. What we're doing fundamentally when we're doing RAG is we're giving the LLM access to new knowledge. We can do this through prompting, one shot, two shot, few shot. We can more specifically do it by providing that data in the vector store. One of the big problems with LLMs is that they don't know what just happened because we trained them a little while ago. So they don't necessarily know about Llama 3 yet. So we chunked up the blog on Llama 3 and fed it into a RAG system. That RAG system is built using OpenAI models, kind of dated models at this point, to be quite honest with you. Text embedding Ada model and the GPT 3.5 Turbo model. And we can chunk this thing up, see how it works through a similar interface that we saw at Gen Z AI called Chat with your PDF. And for that, we go back to the Wiz.
Yes. Okay. So chat with your PDF. First of all, we're just going to talk about kind of, how we got here. So first things first, let's say we used everyone's favorite, AI tool to ask some questions about Llama 3, right? So we're going to ask OpenAI, how many tokens was Llama 3 trained on? And we get this wonderful answer, Llama 3 developed by Meta AI was trained on a data set consisting of hundreds of billions of tokens. Meta hasn't publicly disclosed the exact number of tokens used for Llama, but is generally in line with other 100 billion to trillion tokens. Now, if you weren't thinking too hard, you might just believe this, right? But it's absolutely just not true. It's not the case that it was hundreds of billions of tokens. I mean, maybe technically, yes, that is true. Many hundreds of billions, but Meta did talk about it, right? So this is kind of the idea. LLMs, they're not always up to date. Llama 3 was a recent thing that came out, but it thinks it knows the answer, and so it confidently lies about the response, right? So this is where RAG can help us. So when we look at our, the release blog for Llama 3, we can see it's tons of information, and we can read all of this, and that is going to tell us what the answer is, right? We have an even easier way to do it, right? Which is with this pattern that Greg's discussed, which is RAG. So you can see here that, okay, so it's 15 trillion tokens, technically over 15 trillion tokens, but it's in that ballpark as per Meta's numbers. And when we look at our chat with your PDF application, we can see, we can upload a PDF file to begin. So we just, save this web page as a PDF and we upload it. And then we can ask questions like, how many tokens was Llama 3 trained on? And what's going to happen is it's going to enter into this RAG pipeline, which involves going through a retriever, which is going to retrieve a number of documents. Then it's going to add those into a prompt and then send them to OpenAI's chat OpenAI endpoint. And we can see exactly how it does that by inspecting that in the prompt playground, which we'll do in a second. But the idea is that we're able to get the correct response, which is Llama 3 was trained on over 15 trillion tokens. This is the same model as we saw be exactly wrong, but we're providing it with information, extra information, right? We're augmenting it with that retrieved information, and it's able to do this a lot better. And it's even able to point us to specific sources in the documents. So I'm going to need to zoom out a little bit. So sorry, you might not be able to read, but the idea is it will point us to different passages in the actual document that relate to where we found this. And we can see the source, so we can click on the source, and that will take us to the blog that was referenced in the first place. And this is the kind of power of that RAG application, is it gets us all of this. And if we click on this little button here just from our front end, we can see, right, the template that it's using. Use the following pieces of context, answer to use a question. If you don't know, say you don't know, don't make up an answer. And then we can see it formatted with both the context that we provided or we retrieved, as well as the user's question. And then we get the response. So this is that pattern of RAG. We're able to take an extra step to add information to our LLM so that it can answer questions about things it doesn't know about, hasn't been trained on, using that in-context learning that Greg was talking about, right? So this is the power of that pattern. And with that, I'm going to pass it back to Greg.
Awesome. That's RAG. So what's next? Well, we've got agents, and again, agents are just a pattern. But we're here to tell you today, agents, they're just fancy RAG. Okay? Don't let anybody tell you anything different. That's the thing that you should walk away with about agents today. Also, agent, agent-like, agentic, these are the same things. Where are you going to put agents? Well, you're going to put them wherever you want to. Remember, we talked about all these different pieces. You can put agents really anywhere. The pattern of agents is that they're not this linear thing. Rather, they are this looping, cyclic thing. The LLM is going to help you decide which tools to pick from your tool belt. This pattern is called the reasoning action pattern, and that is the pattern of agents. This loop, given a user input, goes into the LLM. The LLM might decide, hey, I know the answer. Boom, done. I don't need any tools. I could just use my bare hands, the LLM says. Or maybe it goes in and picks out a tool. It uses the tool, observes what the output of that tool is, leverages that in an ongoing thread, and decides based on that gathered information, do I know the answer yet? If so, boom. If not, maybe I'll grab another tool, and so on until a final answer is achieved. Now remember, RAG was a specific pattern. RAG was a pattern, not a specific thing. What we can do is we can compress RAG into a single little block here. And we can talk about agentic RAG. And when we talk about our agentic RAG build today, we're basically going to take two things, tools, put them together. We're going to do a backup Google search retrieval. That means we're going to use retrieval from archive, the scientific paper repository, with backup DuckDuckGo search. Retrieval, remember? Just like in RAG. So our agentic reasoning action loop is going to look like question goes in. We have a setup of a prompt template and access to tools, have a conversation with a human answering the following question, tool 1 prompt, tool 2 prompt, and we'll get a conversation going on our agent scratch pad. This will have access, of course, to our LLM, and we'll go back and forth as many times as we need to through this loop to decide if we know the answer to this question before we finally provide it. This, friends, is the agent, and we'll see how it works briefly. Agentic RAG with the whiz.
Oh, yeah. Okay. So in the last one, it was pretty straightforward. We had questions about Llama and we wanted to ask questions about Llama. This one's a little bit more involved, right? We don't necessarily know even what we want to ask questions about. So let's just see. So we're going to understand this is hooked up to archive and DuckDuckGo. First, we're just going to ask, what is QLoRa in, I'm going to say in, let's just say generative AI. So we type it up and it's asking us, hey, do you want to use DuckDuckGo search? Sure, yes, let's use DuckDuckGo search. So it has the ability for us to sit in a loop and indicate which tool we want it to use. It says, okay, it stands for this. Okay, this is neat. The idea is it's determined it needs to use a tool. That tool is DuckDuckGo search. We can even rate it a little plus here because that's a great answer. Then we can say, are there any papers that concern QLoRa that might help me understand better? And we get to send that query. And this time, we haven't changed anything, but it's going to intelligently understand that we're looking for the archive tool. And again, we can click continue. And this is the idea of agents, right? We don't necessarily know what we're going to ask questions about, but we know that there's a number of tools that might be useful to answer a variety of different questions. And so the way that we're going to do this is with this agentic pattern or a tool agent, right? So tool selection agent, and it's going to give us a bunch of papers and their abstracts, including links that we can click on. And when we click on the links, if it will stop scrolling, here and see if I can capture one in flight, we get this idea of it will take us to archive and tell us all about that. So there you go. And with that, I'll pass you back to Greg.
There it is. So you've seen it all today. What did we learn? Well, we learned that fine tuning was all about teaching the LLM how to act. RAG is about giving the LLM access to new knowledge. And agents are about giving the LLM access to tools. And today, we're not saying tomorrow, but today, agents are just fancy RAG. We were all born not knowing. And in other words, as the kids would tell us, maybe even before this session, we've been noobs and we've only had a hot sec to upgrade that. There's lots of nuance that we skipped over today. We'd love to stay in touch. If you have questions, we're happy to stick around for a few minutes. But that's a wrap, folks. Thanks for joining us for today's lightning lesson. We'll see you again real soon.